let's continue our discussion of Taylor polynomials, which, as we mentioned, are going to be used to approximate transcendental functions. Because think about it, polynomials are pretty easy to work with. I mean, we're talking about lines, quadratics, cubics, compared to something like sine x or e to the x or the natural log of x. Polynomials are fairly easy to work with, both by hand or, putting things into the calculator. Well, this whole idea of approximation has been a central part of calculus all along. So think about whenever we first learned to find the area underneath of a curve. So before we did anything with definite integrals, we broke it up into rectangles or maybe trapezoids. And we found the area by approximating it with what we called a Riemann sum. Then we refined that, took the limit of that in order to get a definite integral, in order to get the exact area underneath the curve. Okay, and the tangent lines, as we saw in the warm-up exercise, were another way to approximate a particular function. It gives you, sure, the slope at that particular value. It's the slope of the tangent line, but if we move a little bit to the left or a little bit to the right, we can use the tangent line to approximate the value of a function. Now, when it comes right down to it, whenever you use your calculator to find the value of something, maybe it's the sine of an angle, maybe it's the square root, or maybe it's the derivative at a particular point, you're still finding an approximation. Sure, that approximation is pretty good, it's pretty accurate, but where do those approximations come from? And can we make the approximations even better? Okay, so the tangent lines to a curve at a particular point, they give a reasonable approximation for that function around that point of tangency. But as soon as we move away from that point of tangency, the further and further we move, then our approximation becomes rubbish. And so Taylor polynomials is going to address this this problem, this kind of limitation. Okay, so a tangent line approximation, it had two things in common with your function, as we saw. It has the point of tangency, it shares a point, and the slope. The slope at that particular point is the same thing as the slope of the tangent line. Okay, but what if we gave it one additional requirement? What if we said that it also has to have the same concavity? Shares the point, shares the slope, and shares the concavity. Well, first of all, lines don't have concavity because its second derivative is equal to 0. So that means that we're going to have to increase the degree of our approximating polynomial. And so instead of finding a tangent line, we're going to find a tangent quadratic, right? And essentially that's what we're going to do here in this next example. Example 1a. Find the equation of the second degree polynomial of the form p sub 2 of x is equal to ax squared plus bx plus c, whose slope, concavity, and function value all agree with f of x is equal to e to x at x equals 0. And so the point of this exercise and the following exercises are all going to lead towards a process that we're going to come up with a Taylor polynomial of any degree. But we got to start someplace. We might as well start with the quadratic. Okay, so let's move on to our first exercise. Okay, we've got example 1. And I'm going to do a couple of things here. The first thing, I'm going to write down our functions. And this is going to be the function, it's going to be the derivative, whatever, the things that we're originally starting with. Function. And so, for example, we're dealing with e to the x. And then we're going to find the function value specifically at x equals 0. So function value. And this is going to be f of 0, e to the 0, which is equal to 1. Fantastic. And now we also want to get a polynomial here to match it up with. And we wanted the second degree polynomial, so we're going to call that p sub 2 of x is equal to ax squared plus bx plus c. And I want to do the same thing that I did with the function value, and that is we want to plug in 0 and set it equal to 1. So p sub 2 of 0 should be, I'd plug 0 in for x, it would go away, and the other x, it would go away, and I'd just be left with c is equal to 1. Bam, I've already got one piece of information for my polynomial. All right, let's move on to the first derivative. I wonder what the first derivative of e to the x is. Why, I think it's e to the x. And then also plug in 0 into that first derivative. E to the 0 is still 1. And now let's take the first derivative of our polynomial. So coming back up here to this level, just using the power rule here, I'd have 2ax plus b. And let's do the same kind of thing. We're going to plug 0 in for x. And my 2a times 0 is going to disappear. I'm just going to be left with b is equal to 1. Now don't get the impression that it's always going to be 1. That's just not the case. All right, let's do it again, shall we? Because we want concavity. So we have a point value. We have a slope value. We need a concavity at that particular point from the second derivative, which is still e to the x. The function value there is still 1. And then whenever I take this was supposed to be the first derivative. The second derivative, I'm going to get 2 times a. Whenever I plug in 0, I get 2a. There's nowhere to plug in the x. This is supposed to equal 1. Dividing over the 2 gives me a is equal to a half. All right, and now I have enough information to rewrite my second degree Taylor polynomial. Right, I just use the a, the b, and the c value that I just found. And kind of like I wrote the equation of the tangent line, I'm going to write it in reverse order instead of in standard form. So this p sub 2 of x is equal to, let's see, our c value was 1, plus our b value was also 1, x, plus our a value is a half, 1/2 x squared. All right, there you go. So that process is not too bad, but you can imagine it's going to get sort of tedious as we increase the degree of our function. I wonder if there's a simpler way. Probably. Okay, so here is now the graph of the approximating polynomial right there in green, that green quadratic. And you can see that it, like if you try to zoom in on it, it's going to be closer than the line is for a lot longer, over a longer period of time or a longer interval. Okay, so we use the tangent line to approximate the value of a function. We're going to use the second degree Taylor polynomial to do the exact same thing. Use p sub 2 of x to approximate f of 0.5, so in other words, the square root of e. And then what's the error in our approximation? Okay, let's come back over here, and we want to find p sub 2 of a half is equal to what? Yes, that's right, it says half. Okay, 1 plus a half times a half squared. Right? And like in terms of AP tests, that would be perfectly acceptable as an answer, as a safe stop, especially if it's a non-calculator question. But I'm going to go ahead and keep going with this. So 3/2 plus a half times a fourth. 3/2 plus an eighth. So 3/2 we can rewrite as eighths by multiplying by 4. I'd have 12 eighths plus 1/8. I get 13 eighths. All right, I'm going to do this without a calculator, old-fashioned style. Divide 8 into 13. Okay, it definitely goes in one time. 1 times 8. Subtract these guys. I've got 5. Put a decimal there. Bring down a 0. Let's see. 8 goes into 50 6 times because that's 48. Subtract. We get a 2. Bring down another 0. So now it's going to go in there 2 times. 2, 16, subtract them 4. Do you remember doing this? It's been a while, hasn't it? Bring down a oops, bring down a 0, 5, there we go. So we got p sub 2 of a half is approximately equal to 1.625. And we want to be able to compare that to e to the, basically the square root of e, which was 1.6, I want to say it was 49, but I'm going to pull up a calculator for that part. New calculator. So let's go to e to 0.5, approximate this guy. Yeah, so a 1.649-ish. So if I take that value and I subtract off the one that we just approximated, 1.625, we get a value of, boop, 0.024 if we approximate. And you can see that our approximation definitely improved. Our error is much smaller than it was whenever we used the tangent line. So let's take a look at some graphs for this thing. So there is, again, the actual function with its function value plotted. So here now is our quadratic, boop, with its function value plotted, with our error of 0.024. And it's so tiny, it is so hard to even see. Look how close it is. And it's much closer than the tangent line was, and it's much closer for a larger interval. Okay, so when we come back, the next one, we're going to make this even better. Why stop at quadratic? Why not try an approximating third-degree Taylor polynomial?